Hello, pre-calc students. We are up to day 2 of Unit 4A. I've titled it here on polynomials. And today we're going to take a look at methods for solving quadratic equations. And these are all methods you should be familiar with. So today should feel mostly like a review, but I would say that it's probably a good review for us. This way we don't jump right into it, assuming that we remember all of these techniques here. So if we take a look at, you'll have to take some notes by hand today, by the way, some methods for solving quadratic equations. We certainly have factoring. And it's a good thing we start the year with a couple days on factoring to remind you of that process. So, I'm sure we can use techniques like GCF, maybe some perfect squares. I'm sure we'll run across trinomial factoring, maybe even with that box method or a slip divide slide if you're familiar with that. Lots of factoring techniques we can use. And this is typically the first thing I want you to consider, because if you can factor something to solve, then that's the fastest way. Now, we also have two other options. Complete the square is something that we saw in the notes yesterday to find the vertex of a quadratic. I'll show you today why it's a method that we can also use to find the solutions to solve a quadratic when set to 0. So then we have quadratic formula as well. Quadratic formula is something that you would have used in Algebra 2 last year to solve and find the values of x that satisfy these equations. And you're in for a treat this morning because I do love to sing the quadratic formula. So I'm going to give it my best shot here on video. I don't know, maybe it will go viral, but let's give it a shot. So quadratic formula, what do we have to fill in over here? The equation is, you ready for this? It's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So there you go. I don't know if you've had teachers that are a little crazy like me that sing the quadratic formula for you, but we definitely have to know and memorize that. This is not something that's ever given to you on a test or quiz. If you have to use quadratic formula, you just got to have that memorized there. So I don't know, what is that tune to? Pop Goes the Weasel, or maybe some other tunes there. But x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So literally that song goes through my head every time I'm using quadratic formula. So I'm sure that if you know that tune, it will probably be going through your head as well. Let's get to some practice questions. So here's the first one. When we solve quadratics, we're solving for x when this is set equal to 0. So we get their first example of 12x squared plus 7x and then minus 12. And to get started here, we're already thinking about, can we factor this at all? And as far as factoring goes, we look for a GCF first. And unfortunately, there is no GCF with 12, 7, and 12 there. So if I continue to think about maybe some box method factoring, the thing that's difficult about having 12x squared and at the end negative 12 is that there's a lot of possibilities, right? I mean, it could be 12x and 1x. It could be 6x and 2x. It could be 4x and 3x. All of those combinations will give you 12x squared. And then think about how those same exact factors, 12, 6, 4, and then 1, 2, 3, how those could also combine some way, somehow, to give you negative 12 over here. So there's definitely a lot to play around with. Oh, and by the way, I guess I could put the 3 over there and the 4 over there, right? I mean, it's definitely going to depend on how we want to set this up in the end. The order of some of these things could switch around, and we don't even know if it's factorable, right? We're playing around with these ideas, but we're not even sure if it is able to be factored. So what I'll tell you is that if you're somebody who notices these patterns quickly, if you put 4x here and actually put a negative 3 down here, and then if you put 3x up here and we put a positive 4 with it, that's going to be the pair that we need to give you a total. Remember, what we're trying to build towards here is that these have to add up to 7x in total. So this winds up being negative 9x in this box, and then this would wind up being a total of 16x, 4 times 4. So there's my total of 7x. But notice how, again, that list of all the factors of 12 in really both of these locations, all right, we'd have to consider them in both spots. This is going to wind up being factorable. Certainly not easy to do. So I guess in the end, the nice thing is that even if you can't figure out how to factor it, things like quadratic formula and complete the square will always work. For this example, I'll stick with the factorization since we've already determined that, but this is the correct factorization for this quadratic. All right, so from there, if I separate those factors, remember the way that we're going to solve is you're setting each side equal to 0. So when I set 4x minus 3 equal to 0, you would add 3 and divide by 4 to get x equals 3/4. There's one solution. Over here, we would subtract 4 and divide by 3 to get x equals -4/3. Guys, so my two solutions, and what do these represent? These are the two x-intercepts. This is where we cross the x-axis. So if we were making a complete sketch, which will be a kind of a goal in this unit, we would cross the x-axis in those two locations. Just to kind of classify these solutions, this is something that you might see on the homework. These solutions are both real numbers. They're rational numbers. When something can be expressed as a fraction, it's rational, and then they are unequal to one another. So there are definitely different ways of describing roots, and in this case, it's real, rational, and unequal. There are 4 ways total that we can do this. There's really only 4 possible combinations. I think we'll probably see each case in the notes. Let's go ahead and try another example. So we've got x squared minus 6x plus 9 equals 0. So first thing I want to ask myself is this factorable? And it should be at least easier to determine right off the bat whether or not this is factorable. So are there things that multiply to positive 9 and add to -6? We don't even have a lead coefficient to worry about, right? And it turns out there is, right? It's x minus 3 and another x minus 3. So when I set each of those equal to 0, we would get x equals 3 twice. So this is what we call a double root, and we'll see graphically eventually what that looks like, even though I think you could probably picture it in your head. So if we think about the way we would classify the roots here is that, well, x equals 3 is definitely a real number. It's definitely a rational number, but I hope it's pretty clear here that the roots are equal. They're exactly equal to one another. So we've got a case where they're real, rational, unequal. Here's a real, rational, equal case. All right. Like I said, there are 2 other possibilities. We'll see them pop up in a minute here. If we have the equation 4x squared minus 2x plus 3 equals 0, the first thing we might ask ourselves is, can we use maybe some box method or slip, divide, slide to try and factor this? And I will save you some of the heartache in advance and tell you that this is not factorable. So, we might try and play around with the box and see if we can get some possible factors to work out. But to save us some time in the video and some time with you practicing, I'm just going to tell you right away, this is not factorable. And I'll tell you, out of the 2 methods, quadratic formula and complete the square, I don't love complete the square for this one because you have that lead coefficient of 4. I think it's much tougher to solve a quadratic when you have a lead coefficient if you're going to use complete the square. So let's do quadratic formula just so we get some good practice with it anyway. When I think about what A, B, and C are for the quadratic formula, we would get that A is the coefficient of x squared, B is the coefficient of x, C is the coefficient at the end, the last constant. So we're going to get x equals -b, right? X equals -b, which is positive 2 plus or minus the square root of -2 squared, right? B squared, minus 4ac minus 4 times 4 times 3 all over 2a. So there we go. Plug in your appropriate values for A, B, and C in those locations. And then really all your work from there is surrounding simplifying that radical, right? Cleaning up what's underneath here and then kind of going from there. -2 squared is 4. These 3 things would multiply to 48. So we get 4 minus 48, which is the square root of -44. And that's all over 8. All right, so from there, how do I simplify the square root of -44? Well, I hope one thing that's jumping out to you right away is that when you have a negative under a radical, the square root of -1 is I. These are going to be imaginary solutions, also known as complex roots. Okay, so I know at least we have that, but radical 44 itself, isn't that just radical 4 times radical 11? Right, 4 times 11 is 44, so that can be broken down to 2 radical 11. Since it was negative, the only thing I'm going to write here is that the square root of negative 44 is the same as 2I radical 11. And that's not the nicest thing to simplify, but it's not the worst either, right? I mean, here's my justification off to the side. The last thing we typically do in cases like this is we separate this into a real number and then an imaginary part. So just divide both things on top by 8. Well, 2/8 is 1/4, right? So it's 1/4 plus or minus, and then it would be 1/4 I radical 11. Typically, when you get roots that are imaginary like this, they're written in A plus BI form. That should sound familiar to you when dealing with complex numbers. They're written in A plus BI form. All right, so what are the roots here? The roots are very clearly imaginary. And I also use the term complex. Okay, those kind of mean the same thing. Complex just means it's of the form A plus BI. But especially when you get that I piece, we know that the roots are imaginary. And once you say they're imaginary, you can kind of stop there. But imaginary roots, I'll tell you, are always unequal. Right? It's this plus the 1/4 and this minus the 1/4 I radical 11. So they'll never be the same imaginary root. But here's what we've got in terms of the solutions for number 3. Certainly a little bit more complicated than comparing it to number 2, but work that should look familiar from last year in Algebra 2. All right, let's do, like I said, we have 4 cases total to look at. So there must be one more. The last example that we're going to look at solving is x squared plus 6x plus 7 is equal to 0. And looking at that right away, I think we get almost lured into thinking that this is factorable. Because you're like, yeah, I got things that multiply to 7 and add to 6. But man, if this was a -7, we'd be in business. Because then we can get multiplies to -7 but adds to +6. Because it's positive, the only factors are +7 and +1, which we would need an 8 in the middle in that case, okay? So since it's not factorable, we are going to either have to use quadratic formula or CTS, complete the square. And I am going to use complete the square for this one for a few reasons. I like complete the square when the coefficient of x squared is 1, which it is. And I like CTS when the coefficient of the x term, the b value, is even. Because remember, we have to divide that by 2 and square it. So when this is an even and this is a 1, I'd really encourage you to keep practicing with CTS. So how do I start CTS? I would move the 7 to the other side. So subtract 7 over here. And then like I just said, take that middle term of 6, divide it by 2 and square it. So 3 squared is 9. And that's what we add to both sides. Okay, so now that we've added that to both sides, the left side is now a perfect square. It becomes x plus 3 squared. The -7 plus the 9 is a +2. I'm going to pause here for a second because if you subtract the 2 back over, if you were to do this, we would know that the vertex is -3, -2, right? Usually there's a y hanging out on this side, not a 0. You know, we're finding the x-intercepts, which is why this is set to 0 right now. But if you move that 2 just really quickly over, we already know that the vertex is here. But leaving it on this side, what the goal is to solve for x. I want to get x alone. So once you write it as this quantity squared, you're now going to take the square root of both sides to continue solving for x. When you take the square root of both sides, it's really important that you put that we have plus or minus the square root of 2 that we're left with. And then that last step is subtracting the 3 over to this side. So the roots are -3 plus or minus the square root of 2. We actually got a lot of information just from completing the square. I really quickly showed you that the vertex is going to happen at -3, -2. And on top of that, we know the 2 x-intercepts. They're not nice places, but if you type these values into your calculator, -3 plus and -3 minus the square root of 2, you can find some decimal approximations as to where those x-intercepts are. Now, what kind of roots do we have here? Are these real numbers? The answer is, yeah, they're real. They're decimals, but they're not rational anymore. They're decimals that wouldn't repeat. So the way you would classify these is that they are irrational roots. And if you have irrational, you'll find that they're always unequal. So being able to classify it's called the nature of the roots. That might sound familiar as a term from last year. Being able to classify the roots, I think, is pretty important. All right, so we've got our 4 examples in there. We've done a little bit of factoring, some CTS, which I think is important to recap. We've done a little bit of quadratic formula. What we're going to move on to now is talking about how do we solve quadratic inequalities. So it's the same type of process, but instead of saying equals 0, we're now going to have less than 0 or greater than 0, something of that form. So to get started, we're going to start with something already in factored form, which is kind of nice. X plus 3 times x minus 4. And we're going to figure out where that's greater than or equal to 0. So what we want to do to consider where this is greater than or equal to 0 is first and foremost, figure out what makes this, what are the zeros? What are the solutions to this? And if you were to draw the wall, you would get x equals -3, and then x equals +4. Okay. So when you get those two solutions as to when this equals 0, your next step is to put those on a number line. And this is a process that we've looked at a little bit already with partitioning, right? So here's what we're going to do. These are our 2 partition points. Because we can consider that this can also be equal to 0, since these are the values that make this equal 0, this expression, we can fill those in with closed circles. And I'm going to now play the game of picking a number in each of these regions and testing to see what happens. Now, here's the thing. When I test, I actually don't even come up with what the number is. We're going to play a positive-negative game, just like we did with linear inequalities. So let's test something to the left of -3. How about -4? -4 plus 3. That's a negative number. I don't even care what negative number it is. Just I know it's negative. -4 minus 4 is altogether negative. So in the end, a negative times another negative is positive. Anything to the left of -3 when plugged into this expression will be a positive number. Let's test 0 in the middle. 0 plus 3, that's positive. 0 minus 4 is negative. Positive times negative, altogether should be negative. And then finally, if I test 5, 5 plus 3 is positive, 5 minus 4 is positive, and 2 positives multiplied together are positive altogether. So now we get to the point of, okay, we've done all this testing, we see where it's positive and where it's negative. What was I actually looking for? What do we actually want? Well, if we want something to be greater than or equal to 0, things that are greater than 0 are positive. So because of this inequality, we're looking for when is this positive? And we know exactly from the number line that it's positive to the left of -3 and to the right of +4. So we're going to get a whole range of solutions that make this inequality true. It's everything from -infinity to -3. Include that with a bracket. And then also 4 to infinity. Okay. So hopefully we're setting the stage for now when we get to examples where maybe it's not already factored for us, we can still easily determine the solutions here. So number 2, I want to figure out when x squared plus 4x is less than 5. Okay, well, it looks a little different than number 1, but what I want you to do first is you have to set this to 0. Okay, set to 0 first. It's important. So I'm going to subtract the 5 over. I really think it's important, just like with the linears, to get 0 on the right side as well. It really helps to make sense of the positives and negatives we're getting up here. All right, and now I have to factor that, and hopefully it is factorable, which I believe this is, right? This would factor into x plus 5 and x minus 1. Those multiply to -5, add to 4 in the middle. All right, so then what did we do once we had it factored? We found the 2 solutions. When does this equal 0? It equals 0 at -5 and +1. So the values that make this equal to 0, we put on a number line. Can I include those values in my end solution set like I included them up here? The answer would be no. Because this is not an inequality where it can also be equal to 0, we don't want to include those endpoints. But now we're going to play that same game of testing values, and I might go a little faster through this one. If I test -6, -6 plus 5, negative, -6 minus 1, negative. Negative times negative is positive. Come over to the middle here. Negative 5 times 1, negative 5 times 1. Let's pick a number. Let's pick 0. 0 plus 5 is positive. 0 minus 1 is negative. Positive times negative is negative. And if I pick 2, 2 plus 5 is positive. 2 minus 1 is positive. Positive times positive is positive. What was I actually looking for? I'm looking for less than 0. So what do we want in this case? We want this to be less than 0, which is negative. And the negative region is everything between negative 5 and 1 without including those. So the way we would not include those is by using parentheses. The solution set for number 2 is everything between negative 5 and 1, excluding those values. All right, so hopefully we're getting the idea. And after looking at these two examples, is it always positive, negative, positive? I don't know if we can quite assume that. A lot of times it is, but I don't want you to assume that. Let's actually take a look at one more together. If we take a look at negative x squared plus 9, I want to know, when is that greater than 0? You have a couple options here as far as how we go about solving this, but I think it would be easier for us to visualize how to factor this if we actually start by dividing both sides by negative 1. So when I divide both sides by negative 1, you have to be super careful, because what's happening here is you get x squared minus 9 now, but we want to know, where is that less than, right? Because if you divide by a negative, we flip the sign of the inequality. Where is that now less than 0? So if we take a look at factoring this to figure out what points am I going to put on my number line to partition around, this is just difference of perfect squares. So the two values that go on the number line are negative 3 and positive 3. We're not going to include those because it's not also equal to 0. And now we're just going to test some points. If I plug in negative 4 plus 3 is negative. Negative 4 minus 3 is negative. Altogether, that's positive. I think this is going to turn out the same way, right? It's going to be that positive, negative, positive again. But let's just double check. If I plug in 0, we get 0 plus 3 is positive. 0 minus 3 is negative. So altogether, negative. And if I test 4, you will get positive, positive at the end for altogether positive. Now just be careful, because what do we want? Do we want positive or do we want negative? You have to go from this last step that we were testing in. Okay, don't go back to the original when it said greater than 0. We changed it such that we made it a less than 0 problem. Less than 0 is we want negative. And the negative is everything in between negative 3 and 3. So that winds up being your solution. Make sure you use parentheses and not brackets, okay? We'll start in our next couple lessons taking a look at this from a graphical perspective, but for now, the algebraic way to solve inequalities is find the solutions, put them on a number line, and use this partitioning process here, all right? So that's our solving equations, quadratics, and when I see you next time, let me know if you have any questions.